Congratulations, you are finished with the electric field for now. We've done the basics, we made the field, we thought about the forces, we thought about the potential, we used Gauss's law. That's the good news. We're done with the electric field for now. The bad news is that means we have to do the magnetic field. The magnetic field. It is so confusing. It's just bad. There's just nothing good about the magnetic field. It's mysterious. It's got sort of a mystique about it, but teaching it and learning it, especially halfway through the class, it's not good. So what I'm going to try to do to help is, I think the problem is how we start the magnetic field usually. We sort of go with this historical introduction. Here's a bar magnet and here's field lines, and don't worry about where they come from. So I'm going to do just one board on the big picture, comparing the electric field, where it came from, what it does, to the magnetic field, where it came from, what it does. And by understanding why you get so confused, it might make you less confused as we go. Okay, so that sounds like a brilliant way to start the magnetic field. So let me just go with this. Like E, the magnetic field, which we call B, and I don't care what happens, I don't even want to answer the question. I don't know why it's B. Okay, so there you go. Don't even ask me why it's B. Is defined by force on charge. So they at least have that in common. They both involve charge. They both involve force. So let's think back a little bit to our electric field. Very straightforward idea. This charge creates an electric field and uses that electric field to create a force on this charge. And really just the electric field was something we made up as a way to describe the force. So Q1 creates E and then pushes Q2. And that's pretty much it. Magnetic field, here's how it's different. For the magnetic field, at this level, the only difference is it's moving. A moving charge creates a magnetic field, and this is just a schematic, that's not necessarily the direction that the magnetic field would be. It creates some magnetic field that pushes a moving charge. Things have to be moving. Okay, so Q1, no, so a moving Q1 creates B, and it pushes a moving Q2. The charges have to move. If these charges are not moving, you just have the electric field and the electrostatic force. If they're moving, you might also have a magnetic field and a magnetic force, in addition to the electric field and the electric force. So when you let the particles move, the forces change. And the new forces that show up, we describe with a new field called the B field. So the two are very much related. We just don't really introduce it that way. It's also, if you think about it, it's a little bit mind-blowing. Here, whose mind do you think it blew? It blew Einstein's mind. So you've heard of Einstein and relativity. So he wrote his famous paper in 1905 about special relativity, and if you try to study that in your freshman physics book, there will invariably be a problem or a thought process about a train and somebody on a train holding a stick or throwing a ball and all this stuff. That's not how Einstein was thinking when he wrote his first paper on special relativity. His first paper on special relativity was called The Electrodynamics of Moving Bodies, his 1905 paper. This is what bothered him. If here is a charge, say, let's not even have this diagram here. I wasn't there, this is maybe exactly what bothered him, but this is kind of the idea. If Q1 is sitting there, and I'm standing here, and I look at it, I see an electric field. And now if I start moving, now Q1 is moving relative to me. So suddenly I see a magnetic field. And then I stop, oh no, it's just an electric field. Then I start moving again, and I see a magnetic field. So the fields that you see depend on your inertial reference frame, as they say. It depends on the relative motion between you and the charge. that's strange. And if you throw in light, which was known to be an electromagnetic wave, things become even more problematic. So it was really these kinds of ideas, why you have E and B is only there when things are moving. That's one of the things that really pushed Einstein to think about relativity. So this is, you know, deep, heavy stuff. I'm not telling you this is trivial. But I think if you can think about it a little bit this way and realize this is what's happening, it might help you see where we're headed when we do the historical introduction. Another difficulty is in math. So what is this force? This push is a force. So what is it? Well, I'll write it real quick just to show you what's coming here, is that the force, I'll just give myself a little room here. The force on a charge, we know the electric part is QE. Use the big Q. Is the charge times the electric field. That's how we defined it. And we just have to multiply a scalar times a vector to get a vector force. But then the magnetic part is also the charge, Q, but then we have to involve the velocity and the B field, and those are both vectors. So we have to multiply out two vectors to get a vector. So you can't do that by just, you have to, how are you going to multiply them? So dot product doesn't work because that gives you a scalar. So when you multiply two vectors and you want to get a vector, you use a cross product. QV cross B. And we'll talk about what that is if you don't know what the cross product is. But what it results in is just conceptual difficulty. The electric field, if the electric field is facing that way, it pushes that way. If the electric field's up, it pushes up. This cross product makes the B field push things sideways. Right, so the B field is this way, the velocity is that way, it pushes this way. So you really have to think in all three dimensions to do the B field problems. And then it does worse things. It causes things to go in circles. Everything's all loopy with a magnetic field. Okay? So prepare for all of these problems and be thinking about them in the back of your mind as we start the more normal introduction to the magnetic field.